example. And again, I encourage you to go back and look at the video that kind of overviews the beam deflection stuff before jumping into this, so you kind of understand what these quantities are. But essentially, we're given a cantilever beam. It's subjected to an end load of P, and results in a deflection equation that looks like this, where y of x being how far we are along the beam and y being how much the beam is deflected, follows this equation. And it wants us to determine the deflection at the end of the beam and the slope at the end of the free beam. So easy enough to do that. We set up so again, given our picture, we've got cantilever beam attached at one end. We are applying a load P down here at this end. It's going to deflect along y based on this equation, and how much the y is deflected will vary depending on what x is, and we want to find out what those are. So part A, we just need to find y of L, so we can just simply plug that into the equation. We have our constants P. We don't have a value for that. We're just going to use that as a generic term. Deflection rigidity, also, we don't know. This 6, again, just kind of comes out from being able to do the expression. We'll plug in L for our length at x, because we're looking all the way at the end of the beam. We know that the first part of that is going to stay the same. It's still going to be P over 6E times I. Inside the expression, we get L cubed. When I multiply that together, I get negative 3 L cubed, so I end up with negative 2 L cubed. And so if I simplify that a little bit, I get negative P times L cubed divided by 3 EI. And again, it's all in terms of variables because they haven't given us specific numbers for the rigidity or the load or any of that sort of thing. Another key point is we should expect that it's negative. We expect that if we're putting a load here, that it's going to deflect down. So at least a reasonable answer there. Okay, so part B asks us to determine the slope at the end of that, at the end of our line. So what is the slope at theta L? And so remember, for slope, we use theta. And then we also remember from the previous video or previous work that the slope is the derivative of our position function. So we have to take the derivative of our expression. So I'm going to write it down here because we're going to be using a different page anyway, so we should be able to complete all this. So we're taking the derivative of x cubed, we're taking the derivative of, should leave the constant in there for now, times x cubed minus 3L times x squared. So I know I can just pull all those constant parts out front. And then if I'm taking the derivative of what's inside the parentheses, I remember I can just do each part and add those back together. So derivative of x cubed is going to be 3x squared. Remember, bring it down front, multiply by the new power. Derivative of 3L times x squared is going to be the 3L and times the derivative of x squared, which is 2x. So I get the expression for theta of x is equal to P over 6 times EI. I get 3x squared minus 6L times x. And then I just have to solve. I want to actually know what is the value at L, so I can plug that in. I get negative 3L squared here inside the parentheses. So I can simplify that a little bit, cancel out a 3, and I end up with negative p L squared over 2 EI. And again, test for does it make sense? I get a negative value. I don't know how large it should be. That's, but I get that it is, since it's at the end of the beam, it does look like the slope would be negative there. In addition to, of course, the value. Of course, we're not only are we deflected to the negative area, but we also seem to have a negative slope there. So that seems like it would make sense to me.